Chapter 4, Chemical Quantities and Aqueous Reactions. So your book uses the example of greenhouse gases. It's a little bit of a theme that goes periodically throughout. You've probably heard about this in the news. Greenhouse gases are important. They're called greenhouse gases because they kind of act like the roof on a greenhouse, where they allow the sunlight to come in, and then they bounce back some of the heat. They trap some of the heat so that it doesn't just get released. And so basically they're like a blanket that's keeping our planet warm. But we don't want too many greenhouse gases because then things can get too warm. If we get too few, then it's going to get too cold and we could plunge into another ice age, and that would be no fun. So we got this balancing in and out energy from the sun. So since 1860, here's a graph. They've measured a 0.7 degrees Celsius rise in average atmospheric temperatures. Now, this graph looks alarming, doesn't it? You're like, oh my goodness, it's going straight up. This is carbon dioxide concentration in parts per million, so going from 290 to 400 parts per million. And here's the temperature variation, which also looks a bit alarming, but this is going from minus 0.4 to 0.8. So that's all of 1.2 degrees Celsius difference between the high and the low of that graph. And I kind of want to talk about this because if you know a bit about science and data, then you can avoid being overly alarmed by some of the stuff you see in the news. Because I look at this graph and I say, well, yeah, there seems to be a trend here, but each of these blue points is the measurement of the average temperature, the annual mean, and then they've averaged it over 5 years and they're giving us this line. There's a lot of variation in there. The train agrees with me. But we see that, there's sometimes even like a 0.3 degree change from year to year. And so then is it that alarming that there's been a 0.7 degree change over this long span of time?
But isn't it just like one degree Celsius that makes a huge impact?
Well, a small temperature change can make a big effect. But the question is, how did they measure this data? How accurate are those measurements? Because the temperature in my front yard is not the same as the temperature in my backyard. And so it's entirely possible that there could be some systematic errors in how they're measuring temperature. It depends on what time of day you measure it and, exactly how that data was averaged and, how the statistics were done on it. And so I see something like this, and I don't just automatically say, oh, it's true. I have more questions because I'm a scientist, and I want to know, well, exactly how did you do that? And if this is good scientific data, you can look it up somewhere, and they will tell you in great detail exactly how they did it, which is what we're learning how to do in our lab notebooks, to write down how we came up with this answer that we're sharing. So we observe that this trend in carbon dioxide is going up and that the temperature change is going up. And then we have to ask ourselves, are the two trends causal? Is the CO2 concentration change causing the temperature change? Or is the temperature change causing the carbon dioxide change? Or are they even related? Did you have a question?
Well, I was going to ask you, because you said that maybe you would be skeptical of the data, but I mean, the fact that the graph shows upward trends during points of industrial revolution, and the fact that it trends upwards over a 130-year period, doesn't that eliminate the possibility of intentionally misconstruing the data?
Well, I'm not even saying that they're intentionally misconstruing. That's a whole other thing.
Well, even accidentally.
Even accidentally. But what about this data from 1880?
Yeah, look, the bump. I mean, it corresponds with the American Industrial Revolution, which
But
is what
how
you would
accurate?
expect.
How accurate were their thermometers?
I mean, there's no reason to assume they were any less accurate than they were today because they operated off of the same mechanics that they do today, and the process hasn't been changed.
Well, but in the old days, they generally made thermometers with mercury, liquid mercury, and now we
Right.
use like piezoelectrics and digital thermometers based on semiconductors. And so we do measure temperatures in a different way. In theory, they should be exactly the same. But all I'm saying, I'm not saying that this is wrong. I'm just saying I have a lot of questions about the graph.
Okay, I was just curious.
Yeah. And so, it's good to have questions. It's good to be a little skeptical. You don't throw stuff out just because you don't like it. I'm not going to say, well, I don't believe in global warming, and so this must be wrong. But I am going to say, tell me exactly how you did this. And are you averaging the same places on the globe? And what if we looked at individual continents separately? And I mean, there's all kinds of things you could do. Pardon me?
Are they biased?
Well, yeah, and then are the scientists biased? Because what happens when a scientist is biased, which is very easy to happen, you have this idea, you have this hypothesis, and you may have big funding motivating you to prove that your hypothesis is correct. That taints how you see things. And the thing about data is there's all these different statistical tests you can do, and if you don't like this one, you can decide, well, I'm not going to use the Grubbs test anymore because that didn't support my data. I'm going to use this other test that lets me keep this point that I think is important. And so you get stuff like that, and it's not as simple as the graph would let us believe. So what does this have to do with this chapter? Well, one source of carbon dioxide is the combustion reactions of fossil fuels. So here is a sample reaction of burning octane. Octane reacts with oxygen when it's burned and produces carbon dioxide and water. And so that is a source of carbon dioxide in the atmosphere. Another source of carbon dioxide is volcanic action. So volcanoes, even when they're not actively erupting, they're spewing gases into the air, and a lot of that is CO2. So how do we figure out if this global warming that seems to be caused by increased CO2 levels is caused by natural sources or by our fossil fuels? We'd have to come up with some way to measure what's going on, right? We can't directly measure the amount of CO2 produced by fossil fuel combustion because it's happening all over the place, right? They can estimate the amount of CO2 produced by volcanoes because you can actually go to the volcano and sample the air and measure how much is coming out. Now, is that going to be a super exact number? No, but at least it gives us an idea. How could we figure out how much is coming from fossil fuels? Well, this chemical reaction, this chemical equation, gives us the exact relationship. 2 molecules of octane are going to react with 25 molecules of oxygen and produce 16 molecules of CO2 and 18 molecules of water. And we can also look at this in terms of moles, because that's just like doing it in dozens would be multiplying by 12. If we just multiply everything by Avogadro's number, we've got moles. So 2 moles of octane react with 25 moles of water, oxygen, produce 16 moles of carbon dioxide. Now, octane is not the only fossil fuel that is burned. But, we're kind of having to just pick one as sort of an average kind of hydrocarbon that's in those fossil fuels. So the amount of every substance that's used and that's made in the chemical reaction is related to all the other ones. we've talked about the law of conservation of mass. You don't create or destroy matter in a chemical reaction. We talked about balancing equations by balancing the atoms, because those atoms, those building blocks, are not created or destroyed, they just get rearranged. So by looking at the mole ratios of octane and CO2, we can also get information about the masses. Well, what if I burned 100 grams of octane? How many grams of CO2 would be produced? We can figure that out from the chemical equation. And this study of the numerical relationships is called stoichiometry. So stoichiometry. And this is a very important topic in chemistry. So these coefficients give us numbers of molecules or atoms. They give us moles. And from the equation, we can get a mole ratio of any two substances. We can look at octane to oxygen. We can look at octane to CO2. We can look at O2 to water. We can look at CO2 to water. Any two we can combine. Everybody okay with that? So we could get a ratio of 2 moles of octane to 25 moles of oxygen. All I'm doing is I'm inserting the unit mole. So I'm just inserting mole in there. So it's 2 moles of this for every 25 of that. It's 25 of this for every 16 of that. Okay? Let's switch from burning fossil fuels and talk about pizza. I hope you guys eat lunch. The number of pizzas you can make depends on the amount of ingredients that you have. Right? So here's a very simple pizza recipe. 1 crust, 5 ounces of sauce, 2 cups of cheese, put them together, you get 1 pizza. And we can express that relationship mathematically. We can say that we need 1 crust for every 5 ounces of sauce, for every 2 cups of cheese, for every 1 pizza. And so we could use those ratios to figure out, well, if I had 2 cups of cheese and plenty of everything else, how many pizzas could I make? Well, a lot of you can just think about it and come up with 5, right? Well, let's think about what we're doing in our head. We're saying, I have 10 cups of cheese. And I want to know how many pizzas can I make. We can do dimensional analysis to solve this problem, which you probably don't need to do with cheese and pizzas, but when we talk about moles of octane and grams of carbon dioxide, it's not going to be as obvious, and so we need our dimensional analysis. So for units, I want to put cups of cheese in the denominator so that those will cancel out, and I want pizzas on top so that that's the unit that gets left. The numbers for this ratio come from the equation. There's a 1 in front of pizza, so 1 pizza. I need 2 cups of cheese. And so I get 10 times 1 divided by 2 tells me I can make 5 pizzas. Any questions? This is exactly what we're going to do using moles. Moles of compounds, moles of elements. The ratios of coefficients in a chemical reaction act as conversion factors. And we can use these to relate any two reactants or products. So if we burn 22 moles of octane, C8H18, how many moles of carbon dioxide form? We're going to look at the balanced chemical equation, and we're going to find the conversion factor and use that. So if we looked at the path, we would have, we're starting with 22 moles of C8H18, and we're trying to figure out how many moles of CO2. You can go from this to that in 1 step. Conversion between any two reactants or products is just 1 step from the chemical equation. 22 moles of C8H18. And in these problems, it's really important to write moles of what? So on the top, I want moles of CO2, because that's what I'm trying to figure out. On the bottom, I want moles of C8H18, because that's what I'm going to derive. You know, if you're making cookies or something, and you don't label cups and teaspoons of what? It's like, well, I need 3 teaspoons. 3 teaspoons of what? Baking soda? Salt? Sugar? Cinnamon? Who knows? It's important to say moles of what. So we put the units in first, and then we look for numbers. For CO2, we find it in the equation. We find the number in front of it, and that's the number that goes in front of it in our conversion factor. What number goes in front of C8H18? 2. That's not hard, is it? So then I just get out my calculator. I've got 22 times 16 divided by 2. And my calculator says 176. The unit would be moles of CO2. Any questions? I have a question. What about significant figures? How many sig figs does this 2 have? Infinite. Because this equation gives us relationships between individual particles. 2 molecules form 16 molecules exactly. And the mole is a counting unit. So these whole numbers from the balanced chemical equation are exact. They have an infinite number of significant figures. And so what we do is we just don't even have to look at them in terms of sig figs. So I started with 3 sig figs. I end up with 3 sig figs. Yes?
So if we were to go further and make the moles of CO2 and the grams of CO2, that's when sig figs matter?
Yes. If we were to go farther and convert this moles of CO2 into grams of CO2, then the number of significant figures in the molar mass that we use could come into could be important. Any other questions? Let's make sure I didn't skip something by accident. So moles are great and all, but we can't measure things in moles. We measure in grams. And so this is our general plan for stoichiometry calculations. Mass of A to moles of A to moles of B to mass of B. If I had grams of C8H18 and I wanted to know how many, come on pointer, how many grams of CO2, I would go grams to moles to moles to grams. What we just learned how to do was the part in the middle. We learned grams to moles and moles to gram in chapter 3. So now we're just going to put these 2 things together. So that's how your book says it. This is how I like to express it. Grams to moles to grams. And that's like the theme of stoichiometry. And just chant it to yourself. You know that you're really getting it if you wake up in the middle of the night muttering grams to moles to moles to grams, right? Then you know, okay, I'm probably studying enough now. Grams to moles to grams. That's the path, okay? We'll see some variations on that later, but this is the basic path. In the middle, we always have moles to moles, because that's how you get from one substance to another substance, is through the chemical equation. So let's do an example. It's got a lot of words. According to the U.S. Department of Energy, the world burned 3.1 times 10 to the 10 barrels of petroleum in 2010, the equivalent of approximately 3.5 times 10 to the 15 grams of gasoline. calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. And there's the equation. And then we're asked to compare the result. Volcanoes produce about 2.1 times 10 to the 11th kilograms of carbon dioxide per year. How many significant figures in this barrels of petroleum? Just 2. Okay. This is not an exact number by any stretch of the imagination, right? There's a lot of uncertainty. But it's a ballpark number, and it'll give us an idea. So another assumption that we're making here is we're going to use the combustion of octane. We're going to assume that it was all octane and calculate it that way. So this is going to be a real rough calculation. So what do we want to find? Mass of CO2. So I want to find mass, and mass is often expressed in what? Grams. So I'm going to write question mark grams under CO2. So that's where I'm ending up. The starting point's a little iffier here, because I've got these two numbers. I've got barrels of gasoline, barrels of petroleum, and I've got grams of gasoline. And gasoline doesn't show up in this equation at all. But this is saying, using the combustion of octane as the representative equation. What that means is we're going to assume that this 3.5 times 10 to the 15th grams of gasoline is all octane. So if we had, yeah, my stylus just leaped out of my hand. But it didn't get away. I caught it. 3.5 times 10 to the 15 grams of octane. So I'm going to get rid of this second part down here because I need a little space. We'll come back to that later. So I need to get from grams of this to grams of that. The path is grams to moles to moles to grams. So it's going to be grams of the first thing to moles of the first thing to moles of the thing I'm trying to find out about, the CO2, and finally grams of CO2. It sounds like they're doing fun things in the lab next door. Any questions? I don't want to go to moles of oxygen or moles of water and then to moles of CO2. You could, but it's extra work. Just go from the compound you know something about to the compound they're asking you about. Now that I have the path, this is just dimensional analysis. I'm going to write things out in my equation like we've always done. 3.5 times 10 to the 15 grams. Again, very important to write the chemical formula there. It is tedious. I know it is. I don't like doing it either, but I like getting the answer right. So I have 3 arrows. I'm going to have 3 conversion factors in here. So I'm going to go to moles of the octane, and then I'm going to go to moles of CO2, and then I'm going to go to grams of CO2. Units from the path and the numerator of each of those terms. And then we put the units in so that they cancel out. So that unit comes down here to cancel out. Moles of C8H18. And there, those cancel out, and this is grams C8H18. So we need numbers for 3 terms. I like doing the easy one first. The middle one's easy. All I have to do is look at the balanced chemical equation. I've got moles of CO2. There's a 16 moles of CO2. So I write 16 in here. 16 moles of CO2 come about from 2 moles of octane burning. So I'm going to write a 2 down here. Where do I get the numbers for the first and last term? I need the molar mass. I'm looking at this with its 2 sig figs, and I'm thinking 4 sig figs in my molar masses is going to be plenty. So for CO2, I've got 12.01 plus 2 times 16, so that's 44.01 grams per mole. So for CO2, 44.01 grams per mole. And for octane, C8H18. I've got 8 carbons times 12.01 plus 18 hydrogens times 1.008. 8 times 12.01 plus 18 times 1.008 equals 114.224 grams per mole. That would only have, well, depending on your point of view, 4 sig figs or 2 decimal places. This is not going to limit my answer, because my answer is going to be limited by the 2 sig figs in there. So one way to deal with significant figures is, if you just identify that this is not going to limit it, you can just write the full thing in there, and then you don't have to worry about it. Thank you. So 1 mole, 114.224 grams. Oh, I thought I was going to close the door. Okay, 3.5 EE15 divided by 114.224 times 16 divided by 2 times 44.01 equals. That's going to have 2 sig figs, and so that's going to be 1.1 times 10 to the 16th grams of CO2. Any questions? Does that make sense? Got some nods. I got some people staring off into space. Yeah, my calculator is 1.07882757. I'm asked the mass, and so that is a final answer. I'm rounding it to 2 significant figures because of the 3.5 times 10 to the 15th that I started with. There was another part to this problem, though, wasn't there? Let's see if I can unearth that. That's just fun. It's like one of those little magic books that you'd go over with a pencil and this picture would appear. Okay, so they're asking us to compare that to how much volcanoes gave off. Well, this is in grams, and that's in kilograms. So I need to convert one to the other. I'm going to convert my grams to kilograms. So 1.1 times 10 to the 16th grams of CO2 times 1 kilogram per 10 to the third grams. And so that's going to be 1.1 times 10 to the 13th kilograms of CO2. So that's more than the volcanoes, right? It's not really obvious how much more. 1.1 times 10 to the 13th, if I divide it by 2 times 10 to the 11th, is 55 times more. So even with, some soft numbers here, it's definitely more. So there's more CO2 being put out into the atmosphere by combustion of fossil fuels than there is by volcanoes. Any questions? Does this calculation prove anything? It doesn't prove anything. Does it suggest that maybe humans are causing the problem? Yeah, it does suggest that. So we've got the petroleum combustion, 1 times 10 to the 16th grams. Here I did it the other way. I went to grams instead of kilograms. Volcanoes, 2 times 10 to the 14th. So it is more. Let's do another practice question. The whole thing with the carbon dioxide, that is to help make this part of chemistry perhaps a little more relevant to real life, to show you that these sorts of calculations can be useful outside of the chemistry lab. I'm not going to quiz you on levels of CO2 or global warming or anything like that. Let's do another example. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, which is primarily HCl, according to the reaction. It's given here. What mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? So this is a very typical stoichiometry problem. You need the balanced chemical equation. Oftentimes it will be given to you. And then read all the words. This part at the top, information, kind of background information, kind of the story of the problem, not necessary to actually solve the problem. This is the real question down here. I'm going to use the balanced chemical equation to organize the information that I've been given. So what mass of HCl in grams? That's the question. So I'm going to find HCl in the equation, and underneath I'm going to write question mark, what mass, grams. That's what I'm trying to find. Is neutralized by containing 3.26 grams of MgOH2. So this is my starting amount. So under MgOH2, I'm going to write 3.26 grams. What's the path for stoichiometry? Grams to moles to moles to grams. So as you're first starting out, you're going to want to write it down. Grams of MgOH2. It's the one that has the number. To moles of the same. Then to moles of the thing that has the question mark. And then to grams of the question. Any questions about the path? Grams to moles to moles to grams. In the first step, we're changing the unit. We're changing from grams to moles, but the compound stays the same. In the last step, we're changing from moles to grams. The units are changing, but the compound stays the same. In the middle, the unit is the same, moles, the compounds are different. You can only change one thing at a time. You can't change two things at a time. So now I'm just going to break out the dimensional analysis and do it. So 3.26 grams of MgOH2. 3 conversion factors. The first one, I'm going to moles of my starting compound. And then I'm going to moles of HCl. And then I'm going to grams of HCl. Down here I've got grams of magnesium hydroxide to cancel there. Moles of magnesium hydroxide to cancel here. Oops. And moles of HCl. The middle term I like to do first because it just comes from this equation. So in front of magnesium hydroxide there is no number. I understand that to be a 1. And so I could leave it with no number down here, or I can write the 1. Multiplying and dividing by 1 doesn't change anything. In front of the HCl there's a 2. So I put the 2 in here. First and last terms are molar masses. We do a lot of calculating molar masses. So magnesium, 24.31? Yeah. So magnesium is 24.31. How many oxygens in that formula? 2. 2 times the mass of oxygen. How many hydrogens? 2. So 2 times the mass of oxygen. 24.31 plus 2 times 16 plus 2 times 1.008 equals 58.326 grams per mole. As I'm looking at sig figs for this, these are exact, the mole ratios. My starting number has 3. This molar mass is not going to limit the number of sig figs in my answer. 58.326 grams per mole. And then I need HCl, 1 hydrogen and 1 chlorine. And I'm going to get 36.458 grams per mole. And that's not going to limit my sig figs either. Any questions? When you put all the units in first, then you don't have to think about, am I supposed to multiply or divide by that molar mass? The molar mass number is the mass of 1 mole, so the number always goes with the grams. 3.26 divided by 58.326 times 2 divided by 1, not divided by that, times 36.458 equals. My answer should have 3 significant figures. It's okay to round it here because this is the final result, 4.08 grams of HCl. Any questions? I have a question. How warm is it going to get in here? 76. Yes. Well, it's so loud. It's 1:19, and so I think we should stop here. What do you think? Go with that?